Alright, today we're going to learn about units. Why are units important? Units are important because if I just write 4 has no meaning other than that there's a 4 right there. But if I say I have 4 apples, that gives meaning to it, right? Now I have 4 apples. What if I said now I have 4 apples per second? So that's more of a rate. Apples per second. The slash mark will always be per. It's probably better to always write it like this so that they're easier to understand. So now, say I wanted to use this for something. Now I have a way of determining, okay, so if I have 4 apples per second, right? And then I wanted to know how many apples there would be total after 10 seconds, right? So that seconds is basically over a 1. If I multiply these two numbers together, the units for the seconds will cancel, and I'll get the total number of apples that I received or that came out of the conveyor or fell off the tree. Who knows? And I'll just have 40 apples. Okay? So where this becomes important is in equations like PV equals nRT. The units on both sides of the equal sign have to be the same. So what shows up over here after I go through and multiply all the units out has to be the same as what's over here. And this is where things can kind of get a little bit tricky, because even before I do anything here, I can say that this is going to have units. So P and V will have units of pressure, or maybe dimensions of pressure, volume. And then on the other side, in RT, R is a constant whose units are determined by all of the other numbers. So you're going to have moles and temperature on the other side. And then whatever R would be. So R has to be these units. It has to be pressure, volume, over moles, temperature. Okay? Otherwise, the equation isn't true, right? Because look at where R is. R is right here next to moles and temperature. So you need to cancel out the moles and temperature and just leave pressure, volume. Okay? And that's sort of how you start these types of questions. You have to ask yourself what units they gave you, what ones you need, right? Because for R equal to 0.08205, it's going to be, I think it's ATM liters per mole Kelvin. Okay? I think that's true. Yeah, that sounds right. But another cool thing you could do is say you wanted this constant in terms of pascals, right? So if I wanted it in terms of pascals, I could take 0.08205 ATM, atmosphere, liter per mole Kelvin, and I can multiply it by however many pascals there are per atmosphere. I think it's like 101 Pascal, I think it's kilopascals per ATM, right? And so when I do that, this cancels out, and now I have kilopascals, and that's going to come out. So if I multiply it by 100, it just basically moves it over a little bit, so you get 8.205-ish kilopascals liters per mole Kelvin. Okay? Now say I didn't want it in liters. Maybe I want it in meters cubed, right? So I could take that number, and I need some conversion factor that tells me how many meters cubed there are per liter. I think it actually just moves it the other direction. I think it's 0.001. Don't know. Something to look at. Okay? So now, what I want you to do for homework is take this number, 0.08205 atmosphere per liter mole Kelvin. And I want you to write it with the correct number for kilopascals per liter Kelvin. I want you to write it kilopascals per meter cubed mole Kelvin. I want you to write it as, what's the other unit of pressure? It's that's torr? Is that one of them? Doesn't matter. Kilopascals per feet cubed moles Kelvin. You don't really ever change the Kelvin, and you don't change the mole. Moles aren't written in any other units. Kelvin's not going to work out, because then you get zeros in the denominator. That's why they use Kelvin, because the Kelvin scale starts at 0 and then goes to the right. You don't go anywhere past 0. So try and get this constant written in all of those units using what we just used. So if you want to go from this right here to this, you need something that has kilopascals per atmosphere. Okay? To get from here to here, you need something that has meters cubed per liter. Here to here, feet cubed per meter cubed. Okay? That's all you got to do. That's how units work. Other important points about units. Okay, so say if I give you a random equation, right? So the force of gravity is equal to some gravitational constant. This isn't the G that you're used to using. Mass 1, mass 2 over r squared, right? So, this has units of newtons. So what are the units of every piece of this? This is a mass, this is a mass. Radius is going to be a length, so radius squared would be meter squared, something like that. What are the units of this guy? So work through that problem and figure it out. Remember, a newton is kilogram meters per second squared. That's the units, the formal units of a Newton, right? You're not going to find Newtons over here. You could kind of write these in odd terms, but really what you want to look at it as is kilograms meter per second squared is equal to, you've got kilograms meters squared, what's G, okay? So work on that problem as well. One thing that might get confusing about units is when a common combination of units gets renamed. So for instance, we said Newton is the same as kilogram meters per second squared. Same thing for Pascal. Pascal is equal to Newton per meter squared. But a Newton is kilogram meter per second squared. And so then you can take your Pascal, 1 over m squared, right? So really it's kilogram per meter second squared. Kind of weird. Anyway, don't let that trip you up. Just try to remember that Newtons, Pascals, what's another common one? I don't think you'll see any other ones besides that in this work, but maybe. Just be ready for it. If you ever get confused about what a unit is, you can always look at, so how do I remember that Newtons are kilograms meters per second squared? Well, F is equal to ma. M being mass, it's in kilograms. A being the acceleration. Acceleration is meters per second squared. Acceleration is how fast or slow your velocity. It's the rate of change of the velocity, right? And velocity is the rate of change of the displacement. Displacement being from A to B, right? So if you went from A to B, you would be able to find the average velocity just by taking the meters and dividing it by the time it took to go from A to B. So second, that's velocity, right? Meters per second. Units tell you a lot. You just have to listen to them. And then, to get acceleration, you have to know a little bit more, and that's why they have formulas for that. Because in order to know the average acceleration from here to here, you would have to have v1, v2, and then you'd use that same time. So it would be v2 minus v1 divided by the time it took you to get between them, right? But, so if we work the units out, you can only subtract something with the same units from something, right? Otherwise, it needs to be multiplication or division if they're different units. So you get meters per second minus meters per second divided by seconds, right? And so that will give me meters per second, and that'll give me meters per second squared, okay? So that's how we play around with units. Hopefully these examples and that little bit of homework will make you more comfortable working with units, all right?